Watch this AI generate hundreds of lines of code perfectly, right up until it hits a syntax error and stops completely. This happens because standard large language models are stateless. They operate as single-shot text generators. They receive a prompt, execute it once, and when they encounter an obstacle, they freeze. Verobots is a custom-built multi-agent ecosystem engineered to solve this stateless limitation. It functions as a continuous worker rather than a standard conversational interface. This ecosystem is designed to handle the entire software development lifecycle entirely on its own. Achieving actual digital autonomy means moving past linear text generation. The system requires a continuous, self-correcting execution framework to finish a given job. The Verobot's full-stack agent operates end-to-end. You give it a project requirement, and it plans the architecture, writes the code, and tests the output, entirely without human intervention. Building an agent capable of zero-error autonomy requires three specific structural changes: a recursive verification loop, parallelized memory containering, and collective peer review. To understand how a conversational interface becomes a functional digital workforce, we have to deconstruct this underlying architecture. This flowchart illustrates the AI Recursive Behavior protocol. A task enters the planning phase, moves to execution, and hits a testing node. When the system detects a bug, it follows this loop backward, actively patching its code and submitting it for retesting. The architecture terminates the loop only when every verification node returns a zero-error status. Until then, it iterates. This continuous cycle mimics the workflow of a human engineer. The agent thinks through a problem, verifies the output, and iterates. Algorithmic persistence, rather than raw reasoning capability, is the absolute bedrock of a reliable autonomous agent. Complex tasks require parallel processing. The logistical problem becomes how to multiply these agents without geometrically multiplying your compute and storage costs. Normally, spawning a new agent instance means duplicating massive vector databases. That approach quickly drains system resources and leads to severe latency. This diagram shows AI auto-cloning and containering. When a complex task arrives, the main agent splinters into multiple executor nodes. AI containering isolates only the executor logic, giving each node a distinct execution space. Crucially, the underlying databases remain singular. All splintered containers seamlessly pull from the core memory. Once isolated tasks are complete, the independent results aggregate straight back into the main agent. Isolating compute from memory is the only viable way to scale a multi-agent system massively while maintaining perfect informational consistency across all active threads. There is a specific risk to building unstoppable recursive loops. If an agent hallucinates, an autonomous cycle will amplify that error rather than fix it. This diagram outlines the AI Group Corrector, an automated peer review mechanism. One agent generates an output that deviates from the facts. Immediately, the other agents detect the anomaly, initiate a vote to override it with the correct solution, and simultaneously learn from the mistake. To prevent these errors, we must look at how individual agents retrieve knowledge. Standard AI systems rely on flat lists and nearest neighbor word associations. This animation shows the transition to the Verobot's cognitive organizer architecture. The linear data transforms into a dynamic, tree-like network. Because this structure maps out causal relationships, the agent can logically navigate complex reasoning, discovering connections between seemingly unrelated data. You cannot prompt your way to error-free AI. It requires relational data architecture and structural consensus models built directly into the system. Running these continuous multi-agent loops introduces an enormous financial cost, exponential token consumption, and context window overflow. This visualization shows the custom pipeline used to compress memory. Look at how the block of text is sliced. Instead of arbitrary limits cutting through the middle of words, the algorithm dynamically adjusts. These slices snap exactly to word and semantic boundaries. During an update cycle, the system executes a physical purge. Old chunks are permanently deleted and replaced by a single authoritative version. By combining this precise chunking with physical purging, the platform reduces operational resource and token consumption by over 90%. True autonomy requires extreme memory compression and strict cost optimization. Without it, continuous AI execution simply isn't financially viable. User requests pass through a Go native gateway to the AI dispatch block. Here, a mixture of experts' routing mechanisms selects the most qualified specialized model. Below, the split database strategy isolates transactional logic in MySQL, while PostgreSQL is dedicated to AI knowledge retrieval. By externalizing all AI instructions to the database rather than the source code, administrators can modify agent behavior in real time. This ensures that the massive multi-server infrastructure operates with zero hard-coded instructions. Building a full-stack AI agent demands rigorous, traditional software architecture layered directly beneath these new AI cognitive structures. Systems like Verobots effectively bridge the gap between simple semantic search chatbots and a completely autonomous, zero-error digital workforce. Relentless systems engineering transforms a language model into a reliable, autonomous workforce. True digital autonomy is the result of that optimization, not a property of the model itself.